Hello, fellow problem solvers. So today we're going to be doing a problem from the 2000 German Federal Math Olympiad. This is a cool introductory problem for combinatorics. So I suggest you try this problem out for a minimum of 20 minutes, ideally 45 minutes, but not more than an hour and a half. If on the other hand you'd like to go along with us, I suggest you take 10 to 15 minutes and play around with the problem a bit and try to solve it. So now, let's begin. So the problem says we have weights of 1, 2, all the way through n, where n is a natural number greater than or equal to 3, and it asks us to find every single n for which we can divide these weights into 3 groups such that the weight of the coins in each group is the same. Now say that you have no idea how to begin this, that you never saw this type of problem in your life. Well, the first thing you can do is, in these types of situations where you have no idea what to do, just let's play around. N equals 3, 4, 5, 6, 7, 8, and figure out which of these you can put into groups and which ones you can't. So now I invite you to take 5 to 10 minutes and figure out which one of these work and which one of these don't work. And now we're going to play around. And what we get is that 3 doesn't work, 4 doesn't work, 5 works, 6 works, 7, no matter what we do, we can't seem to get them, and 8, it works. We get a sum of 12 in each one of these cases. Here we get a 7, here we get a 5. Now what I do if I still don't have any idea is I personally will actually go up till n equals 9, 10, 11, 12, 13, 14, 15. Some problems I try to find n, say if I'm doing with sequences, I'll try to find n to a 50. And the thing is to know that, don't overdo this, but still it's important for you to get comfortable not knowing and exploring the problem, trying to figure out how you're going to solve it through exploration. Now, if you still have no idea how you would solve this or what the solution is, I invite you to take another 5 to 15 minutes and play around with these. That's what we're going to be doing now. So what we get is this thing right here. We get n equals 9 is yes, we get 15 in each group, 11 yes, 22, yes for 12, no for 13, 14 yes again. And now for 15 we also get a yes. And now I invite you, after you've played around with this, see what it is you notice. Do you notice maybe, let's see which numbers work. So we have 5, 6, 8, 9, and then 10 doesn't work. Then we have 11, 12, and then we have 14 and 15. So these are numbers that work. So you can see 2. What do all these numbers have in common? Well, I invite you to take now half an hour and try to figure out what these numbers have in common. See if you can use that to maybe solve the problem entirely, or at least construct a solution for these types of numbers. Here's the solution. So what we get is that these are the numbers that work, and they are of the form 3k or 3k plus 2, with the exception of 3. And all of these numbers that don't work are of the form 3k plus 2. And now there's 2 ways to go about this. One is to try to construct all of these numbers first, and the other is to try to prove that no number of the form 3k plus 2 work. Now, I will first try to do this thing, the construction, because it's easier for me. If you haven't attempted the construction, I invite you to take 10 to 20 minutes and try to construct every single partition for n of the form 3k and 3k plus 2. And here's my idea. I have it for 5, 6, 8, and 9. And I know for 6, I have these numbers, 1, 6, 2, 5, and 3, 4. Now, if I add t to every single one of these numbers, t plus 1, t plus 6, the sums remain identical throughout. And now this is where the idea for induction comes in. Say I have a partition for t. Now I can go from t to t plus 6. Why? Well, I'll partition the numbers 1 through t, how they are partitioned for t. And for the numbers t plus 1 through t plus 6, I'll just put these 2 in one group, these 2 in another group, and these 2 in the last group. And this really completes the induction. This completes, now that we have 5, 6, 8, and 9, this means that every number of the form 3k and 3k plus 2, where k is greater than or equal to 2, will work. And now that the construction is done, how do we prove that this is impossible? Well, there's really 2 ways. One is a thing that you usually do, a trick sort of, or a thought pattern that you do when you're trying to solve these types of problems, try to prove an impossibility. So here's the backwards motivation. For 5, the sum in each of the groups was 5. For 6, it was what? It was 7. For 8, it was 12. For 9, it was 15. For 11, it was 22. For 14, it was 35. And for 15, it was 40. Oh, and for 12, it was 26. Is there any pattern that emerges once you look at these numbers? This is one question to keep in mind. Is there any pattern? I maybe invite you to take 5 minutes and figure out if there is. But the other thing is, let's look at it recursively. Let's make that the sum for t. So the sum for 5 is equal to 5, the sum for 6 is equal to 7, and so on. Let's call that st. From our recursive here definition, it seems that st plus 6 is going to be equal to st plus what? Plus 2t plus 7. So what does this tell you about the form st takes? And it has some base values. Well, it tells you really that this is a quadratic. It takes a quadratic form. Now, you can either solve this, or guess what the quadratic form is. Call it an squared plus bn plus c. Let that be Sn. And then figure out what a, b, and c are just from 5, 6, and 8 and the corresponding values. And you'll figure out what a, b, and c are. And this can motivate, once you get that, Sn is equal to a sixth of n squared plus a sixth of n. Namely that Sn is n times n plus 1 over 6. For every single one of these that works, now you can go back to look at, why does 3k plus 2 fail? Why does this fail for 3k plus 2? And I invite you to take now 10 to 15 minutes and try to finish the problem. Well, the reason it fails is because now this is a general sort of thing that you do in problem solving. And the idea is, you see we have the problem into 3 groups. And the general sort of thing to do is to look at the big picture of the problem. Not look at the specifics of these groups, but look at what these groups tell us about the form of the solution or the form of the n that we can take. And the thing is, we don't really have information about what can be in these groups. Like there's a finite number of things, but there's a huge number, I don't know what the correct number is, of ways we can divide these n weights into these groups. So what we can do is, when we sum all these groups up, every single one of them has this weight a, and where 3a is equal to what? Well, every single weight is represented in one group, which means 3a is going to be equal to the sum of all weights. And we know this is n times n plus 1 over 2, which means that a has to be n times n plus 1 over 6. But the only way a works is that if this is an integer. And it's an integer if either n or n plus 1 is divisible by 3. And this thing here is really the reason why for n equals 3k plus 2, we can never partition them, because if we were to partition them, we would need to partition them into groups which have a fractional amount of weights in them, which is impossible because all of these are positive integers. So now I invite you to take 5 to 10 minutes and try to write up a solution. Here's our write-up. So we say this, that we shall prove that n congruent to 0 or 2 modulo 3 with n greater than or equal to 5 works. We deal with n equals 3 separately, and then we say that n equals 3k plus 1 doesn't work because if the sum of each group was a, the sum of all 3 would be 3 times a on one hand, and on the other 1 plus 2 plus all the way till n, which would imply this. And because n is of the form 3k plus 1, this would imply a is not an integer, which is impossible, which means this is impossible to partition. And now we prove that possibility, namely that every single one, every n that's congruent to 0 or 2 mod 3 and that's greater than or equal to 5 works. We say we'll prove this inductively, and our base case is. Namely, our base case is n equals 5, 6, 8, and 9. We assume t works and prove that t plus 6 works. And the way we partition this is, and we write this down, and now this means that all the sums are equal. And here we say that, we conclude finally that n 0 or 2 mod 3 with n greater than 5 is the only n which works. This solves the problem, and as always, thanks for problem solving.